Okay, so good morning, everyone. Welcome back to Math 115. This is day 3. And just a reminder for those of you who might be watching the recording, we have 2 homeworks which are due this Thursday and 1 homework which is due this Friday. Today we're going to cover the material which should be necessary for you to complete A.1 Part B. So after today, A.1 Part A and B should be fully, you should be fully able to do those given what we've covered in class, although it's also review, so if you may already be able to do Part A and Part B just without even coming to class. But if you need the little reminder on some of these things, then that's perfectly fine. After today, you should be able to do those 2 homework assignments. I'd also like to announce the first quiz, which is going to be 1 week from today. The sections which are going to be relevant for the quiz are going to be A.1, A.2, and A.3. Just like the exams, for the quizzes, the problems on the quiz will be taken directly from the homework. Okay, so I'll take one of your homework problems, I'll switch up the numbers maybe a little bit to make it nice, and then it'll be probably like 2 problems, or maybe 2 to 4 problems, I'll say. And that will be your quiz, which will be in the last 15 minutes of class, 1 week from today, in this very classroom. Any questions about homework or quiz before we start?
What's the quiz?
A.1, A.2, and A.3 are going to be the sections which are relevant for the quiz. So that's going to be all the stuff we've done so far, plus integer exponents, polynomials, and factoring is going to be A.2, and then A.3 is going to be rational expressions. Okay, so divide, like talking about fractions with polynomials in the top and bottom. Okay, and you're going to factor them, multiply them, add them, and that's pretty much it. Okay, so let's start on material for today. Actually, why don't I remind you what we were doing last time? So what we were doing last time was talking more about sets, and I recognize that these sets are kind of... why don't I go close this door, actually, so I don't yell out into the hallway. So I recognize that these sets are kind of abstract and a little bit tricky to get your head around at first if you haven't thought about sets much in the past. But I promise that it's going to be very, 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 very helpful to have a good understanding of how sets work, how we combine sets, how we take the intersection of sets, how we do set minus and these sorts of things. I promise that's going to be really, 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 really helpful when we talk about the domain and range of a function. Because the way we're going to express the domain of a function, which is the numbers which we can plug in, we're going to express that as a set. We're going to take our bucket, and what are we going to put in our bucket? All the numbers which are allowed to be plugged into the function. So that's going to be the domain of our function. So I promise this set stuff this is not just like day 1 stuff that's not going to come back. It's going to be used pretty much throughout the whole semester, because we're going to talk about all sorts of different functions and their domains and ranges. Okay, so then we talked about the different sets of numbers, like natural numbers, real numbers. I won't go back into that. The only thing I want to add is that the one thing that I forgot to touch on regarding real numbers as opposed to the rational numbers is that there is also a large class of irrational numbers of things like square root p, where p is prime. Okay, who knows what a prime number is? Can you tell us?
Something that can only be divided by 1 in itself.
Very good, Griffin. It's something which can only be divided by itself. So numbers like 2, 3, 5, 7, 13, oh, I forgot 11. You know, numbers like this which are going to be, well, they're pretty much always odd numbers except for 2. And they're going to be numbers which are only divisible by themselves and 1. So things like the square root of 2 is also an irrational number, okay, or square root of 5, okay, is irrational. These types of numbers are also going to be irrational numbers, so that was the only thing that I forgot to really touch on there. Okay, so then we did an activity and we talked about the real number line, and specifically we talked about graphing intervals. Okay, so talked about closed versus open intervals, and we talked about intervals of a mixed form as well. So something like so is an interval which we would say it's not open or closed. We sometimes use the terminology it's half open or half closed to refer to the fact that on one end we do include the endpoint, but on the other end we don't include the endpoint. So how do we graph it? We do something like this, okay? Or if you want, you can use the closed dot on the right-hand side and an open dot on the left-hand side to graph that inequality, or that interval, I guess. Which an interval is nothing but a combined inequality, right? We say a is less than x is less than or equal to b. So interval is basically an inequality in and of itself. So that was the last thing that we talked about. So we're going to move kind of away from that next and talk about absolute value. But I want to ask if anyone has thought of any questions that they've had about intervals or sets or inequalities or the real number line, anything that came up like while you were dreaming last night that you're thinking like, oh, I should ask that in class today. Yes?
Would it be graded differently for using the brackets or like the dots or anything like that? Or?
No, as long as it's clear to me whether the point is included or not, you can use the bracket notation like the book does, or you can use the closed dot, open dot notation. But if you just, if you just draw something like so, I'm going to be really confused because I can't tell whether 4 and 6 should be included, something like that. Does that make sense? Okay. Any other questions?
Can we
Yep.
just do it above the line to make it clear?
Yeah, that's fine. If you want to do like one of these, something like that to show me. Yeah, as long as it's clear. And if you have a question, just when you come and turn it in, just show me your paper and be like, is this clear? And then I'll say yes or no. Okay, well, let's go ahead and start then. So I started the recording, right? Okay, good. Okay. All right, so let's talk about absolute value. So the absolute value is an operator. Okay, so an operator is kind of like a function, right? So we're going to plug in a number into the absolute value function, and it's going to give us something back. Okay, and the notation we use is we do one of these with bars on the side like this. So just straight up and down bars on the left and right side denotes absolute value. And what the absolute value function does is it kind of tells you what is the magnitude of this number. Who's heard the word magnitude before? Maybe in like a physics class or something like that, right? So magnitude is going to tell us basically the size of the number, okay? And what that means is we're going to ignore the sign of the number, okay? We're only going to care about the size of the number. So if x is larger than or equal to 0, then absolute value is going to do what? It's going to do absolutely nothing. So absolute value of x, if x is positive or non-negative, then the absolute value of x is just x. And then what is it going to do if x is negative? Then absolute value of x is going to be equal to what in terms of x? It's going to be x if it was positive, but x is negative. So I don't want to put x here. What should I put instead? Negative x, right? Because negative is a positive, right? So I'm going to put negative x, okay, where minus x is referring to the negation of x. So it's already negative. So if I negate a negative, it becomes a positive. Okay, so that's absolute value. And so this allows us to measure, say, the distance between 2 points on the real number line. So let me draw a diagram so you can see what I'm talking about. So let me draw a diagram. So let's say we want to measure the distance between 2 points, like 1 and 7. Okay, then I can measure the distance between 2 points on the real number line. Let's call the 2 points x and y on the real number line. The way we're going to do that is by taking the absolute value of x minus y, which is coincidentally the same thing as the absolute value of y minus x. Okay, so this distance operator, we want to be able to take the distance between 2 points, and the distance between x and y should be the same as the distance between y and x, right? Because distance is always positive. So that's why absolute value is always positive, right? Distance is always positive. These two things go together. Okay, so we take the absolute value. And let me show you how that works. So if you take the absolute value of 7 minus 1, then that's equal to the absolute value of 6, which is just 6 by our above definition. But what if we accidentally started at the wrong point? Then we would get the absolute value of 1 minus 7, which would be the absolute value of minus 6, which would be 6 again, right? So this definition makes sense. The distance between x and y is the same as the distance between y and x, and so on. All right, questions about absolute value or distance? Okay. We'll get a more interesting definition of distance later when we're talking about the Cartesian plane, maybe. Okay. So the one thing I want to stress is if you want to say what is the distance between 7 and 1, the answer should never be a negative number. Okay, it should always be the distance between, which distance is always positive. Okay. So next, let's talk about the distributive property. So the distributive property is pretty simple. It just says that if we multiply across a sum, so A times something like B plus C, where A, B, and C are numbers, or functions, or really anything you want, actually. But it might be helpful to think of them as numbers. If we do A times B plus C like shown, then this is equal to, we can distribute. And sometimes what I'll do when I'm distributing is I'll draw these little lines here to show that I'm multiplying each of these things by A. And I get A times B plus B times C. So what does this really mean? This means that I can interchange the order of multiplication and summation, right? Yeah. I'm sorry, yeah, thank you. Sometimes this happens to me when I'm trying to explain a point. My hand is like not doing what my mouth is doing. So yes, if you ever catch me making a silly mistake like that, please just point it out to me right away so that I can correct that. Yes, so we should multiply A times B plus A times C. And it works in the other direction too. So if I do A plus B and I multiply out back by C, then I can kind of reverse, I don't know if you want to call it reverse distributing, but we're going to do A times C plus B times C this time. I think I did it right that time. Okay, so that's the distributive property. I think that should probably be familiar. And another thing that you've probably used before, but maybe you don't remember the name of it, is the zero product property. Does anyone know what the zero product property is? Maybe you think you know, but you're too nervous to raise your hand. That's okay. All right, well, the zero product property says that if I multiply two things together and I get 0, then one of two things must be true. Can you help me finish the definition?
One of them is 0?
Yeah, one of them should be 0, right? Either A is 0 or B is equal to 0. And when do we use the zero product property? A lot. Anybody remember? Well, I use the zero product property a lot when I want to solve something like x squared plus 2x. Why don't I say x squared minus 1 equals 0. And I want to solve for the values of x, which make this true. And so what do? I factor the left-hand side into x plus 1 and x minus 1 equals 0. And then what do you always do? You take each of these two factors and you set it equal to 0, right? But what you're using there is the zero product property. You're saying that in order for this equation to be 0, I know that this equation is equivalent to a product of two numbers. And if a product of two numbers is equal to 0, then one of those numbers must have been 0, which is why you then go ahead and set x plus 1 equals 0 and x minus 1 equals 0 by the zero product property. Okay, so that's what I meant when I say you've probably seen this before, but maybe you don't remember the name of it, or exactly what's going on with it. Okay, so let's talk about basic algebra. So we need to make sure that we know how to solve basic algebraic equations. For example, equations like 3x minus 2 is equal to 4. If we want to solve for x in this situation, what we need to do is isolate it. Okay, and so what we're going to do is basically reverse the steps of PEMDAS. Okay, so the first thing we're going to do is we're going to move the 2 over to the other side, right? So plus 2, and what do we get? 3x is equal to 6. And now to get x by itself, it's being multiplied by 3. So I have to undo a multiplication. The opposite of a multiplication is a division, and I'm going to divide by 3 on this side. Of course, if I divide by 3 on one side, if two numbers are the same, if I divide both of those numbers by 3, then we should still be the same. But if I divide just one of them by 3, then it's going to imbalance the equality, right? So I'm going to divide by 3 on both sides. That's why I have to do everything to both sides of this equality. Okay, and then I get just x is equal to 2. So sometimes I'll draw this little sign here. This is just an arrow, by the way. It just means implies. And sometimes I'll be really lazy and I'll use a single arrow. Okay, so next up we can do this. We're going to talk more about factoring later, but the basic idea, right, is to come up with a number which multiplies to -3. Two numbers which multiply together, we get -3, and if you add them together, then we get 2. So what are those numbers going to be in this case?
3 and -1.
Yeah, 3 and -1. So plus 3 and x minus 1 is equal to 0. And then by the zero product property, we can say then that either x plus 3 equals 0, in which case x is equal to -3, or x minus 1 is equal to 0, which tells us that x would be equal to 1, right? And you can see how if I put in 1 here, 1 minus 1 would be 0, right? Or if I put in -3 here, then -3 plus 3 would be 0. Okay. We'll talk more about factoring in a minute. But any questions about the distributive property, the zero product property, or basic algebra? All right, if not, then let's get on to the meat for today, which is going to be integer exponents. Gotta kill my coffee. Okay, so integer exponents. So let's define what exponents are. I don't really know what I was thinking when I wrote this. It seemed like I was going to put something in here, but I don't know what. Maybe we'll put some examples of exponents. I don't know, 2 to the 4th, 3 to the 6th, stuff like that. But also, integer could be 0 or it could be negative, right? So we could also do something like 5 to the -2, something like that. Okay, so those are some examples of integer exponents. So let's define what it means to use exponents. And the other word we use sometimes to talk about exponents is powers, or to the power of. So that's what I want to, I just like to write down all of the lingo that I am going to use when we start one of these. So the first one is a to the n. Okay, so you're going to notice I'm not going to be doing this in terms of defining what does x squared mean, what does x cubed mean. I'm going to be doing this in general, where a is a number and n should be an integer for now. Okay, we'll learn about rational exponents another time. So if n is an integer, and I take a to the power n, and let's say that n is positive, bigger than 0, and n is an, why don't I just say n is a natural? That's the easier way to say it. N is in n. Okay, so this means n is a number like 1, 2, 3, 4, blah, 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 blah. Then a to the n means we do the following. A times dot, 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 times a, where this multiplication is done n times. Okay, so what do? I line up n. Well, I guess it's not really n multiplications. Well, it's like n minus 1 multiplications, but it's n total a's, right? So if I'm doing a cubed, for example, then I do a times a times a. So if you want to think about that as 3 multiplications or 2, it's up to you. But we've got 3 total a's here, and we're multiplying them all together. Okay. So that's what that means. How about a to the 0? What is a to the 0 going to be? I'm hearing like half saying 0 and half saying 1. Can anybody say why it should be one or the other? Every time we're doing math, we should be able to justify what we're going to say, right? So what do we think? Okay, someone's still confident in 1. Can you tell me why?
Because there's no energy multiplied by, so it would just be by itself.
It would just be by itself is a little bit non-specific. I'm looking for something a little more specific than that. Let's think about the following. There's actually a really good reason why a to the 0 should be 1. Because let's consider the following. I'm going to make a tower of powers of a. And I want to understand, what does it take for me to go up 1 level in this tower? What do I have to do to a squared to get a cubed? Multiply by a, right? What do I have to do to get from a cubed to a to the 4th? You multiply by a, right? And so on. Multiply by a. This is how I go up the elevator. How do I go down the elevator to get from a to the 5th to a to the 4th? I divide by a, right? And I divide by a. And I divide by a. And then if I was at level a to the 1, and I went down 1 further level, what would I do? I would divide by a again. So if at a to the 1, we know that a to the 1st power is just itself, right? So if I divide anything by itself, what should I get? 1. So that's why a to the 0 is always 1. Okay, so a to the 0 is always 1. I guess I'll put in an extra one here, which is that a to the 1 is always a. Okay, so a to the 0 is 1, not 0. All right, how about a to the minus n?
1 over a n.
Yeah, 1 over a to the n. Okay, so again, negative exponent. I'm just going to keep going down this ladder, right? A to the 0. I can do that again. I can divide 1 by a. And then I would have a to the negative 1 would be 1 over a, right? And then I would divide by a again to get a to the negative 2, which would be 1 over a squared, and so on and so forth, right? So a to the minus n is 1 over a to the n. Okay, now for the confusing ones, which I tend to have a lot of students who get these ones mixed up sometimes in terms of how do we combine a to the something times a to the something else, or a to the something divided by a to the something else, and then also a to a power, and then we take that whole thing to another power. So what do we do if we're going to multiply a to the m times a to the n? Well, what we need to realize is this is a times a times a dot dot dot, where we do this m times, right? And then we're going to multiply that times the same thing where we do that n times. So how many total a's am I going to have? I'm going to have all the m ones from the first part plus all of the rest of them from the n part, right? So in this case, when we do a to the m times a to the n, what am I going to get? A to the m plus n. M plus n. Okay. And how about if I do division? A to the m divided by a to the n. Well, you can rewrite addition. Did I say addition? I meant to say division. Okay, so if we do division here, a to the m divided by a to the n could be rewritten as the following. A to the m times 1 over a to the n. Hopefully you agree with me there. And then that can be rewritten as a to the m times a to the minus n. And by our previous rule, it says if we have a to the something times a to the something else, we should add those two somethings. What happens if I add a negative number? That's the same as subtraction, right? So what do I get? A to the m minus n. Okay, great. All right, now we're going to get trickier. What happens if I do a times b in parentheses and then I take all of that to the power n? I'm going to multiply what? Yeah, I'm going to essentially use the word distribute here, but it's not really a distribution. But this power n is going to appear on here and here. Why? Because this is ab times ab dot 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 times ab, where we do this n times, right? And you can see I'm going to have in the end exactly n a's and I'm going to have n b's, right? So since multiplication can be done in any order, I can just rewrite this as a times a dot 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 times a n times, and then times b dot 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 times b n times, which would again be a to the n times b to the n. Was this what you had in mind? Okay. So yeah, we can basically, I don't like using the word distribute, but distribute this power onto each of these. Now, I want to caution you that this is not true if we have something like a plus b to the n. What do I have to do if I do a plus b to the n? Well, I have to rewrite this as a plus b times a plus b dot 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 times a plus b. And if I multiply these first two together, am I just going to get a squared plus b squared? No, what else am I going to have? I'm going to have 2ab, right? I have to FOIL, right? I need to FOIL. If I'm going to multiply a plus b to the n, so the point here is be very careful, because a plus b to the n is not equal to a to the n plus b to the n unless n is 1. That's the only situation in which that would be true. So that's a word of warning. Okay, how about if I do a to the m to the n? Can someone walk me through that one?
You multiply the exponent.
Yeah, I'm going to multiply the exponents. The reason is this is a to the m times a to the m dot times dot 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 times a to the m, where we do this n times, right? And then each of these, we can use the okay, why can I not move? There we go. Each of these, we can use we can use the product rule, Jesus, which says that we're going to add the powers, right? when we're multiplying like so. So we add these powers, m plus m plus m plus m, n times. So adding m to itself n times is the same thing as multiplying m times n. That's all multiplication is. It's repeated addition, right? So we're going to get a to the m times n in this case. Okay, so the one that people always mix up or the ones which people always mix up are these two, where people forget when am I supposed to add the exponents versus when am I supposed to multiply the exponents. So that's just a common mistake. I want to throw it out there so that you're aware that many students make that mistake. Okay, a to the n divided by b to the n. We can use our previous rules to determine that this is going to be a to the n over b to the n. So let's do a couple of quick practice ones. Let's do something like this. 5 over 8 cubed times 8 to the negative 2. So I'm going to try to simplify this as best I can. Well, I know that using the last rule that I just learned, I can distribute that 3. So I get 5 cubed over 8 cubed. And then this is going to be multiplied by, I'm also going to rewrite 8 to the negative 2 as 1 over 8 squared. Okay, so how can I simplify this further? I can multiply these two fractions. We learned on the first day of class how to multiply two fractions. What do? I multiply the numerator times the numerator, and then I multiply the denominator times the denominator. What's 5 cubed times 1 going to be? 5 cubed. And how about 8 cubed times 8 squared? 8 to the 5th, right? I add them. I add the powers when I multiply something like this. Okay, so that's fully simplified. If you want to write it out as 125 over whatever that is, then you can. All right, let's do a more abstract one. We're going to take away the numbers now, and now we're going to use letters. Everyone's always telling me how they hate how there's letters in math, but all of math is letters. Okay, so what are we going to do in this case? We have a few different things to work with, okay? First of all, 15 and 3 have a common factor, right? 3 goes into both of them. So I can cancel out a power of 3 here and make that a 1. And I can cancel out a power of 3 in the numerator and make that a 5, yes? Okay, now how am I going to adjudicate the x's? We've got x to the 5th over x to the 7. What's going to happen? We're going to subtract, so we would have a power of negative 2 in the numerator. But we could also just see, well, we know that there's a larger power of x in the denominator, right? So I'm going to do the following. I'm going to cross out this 7 here, and I'm going to cross out this 5 here, and I'm going to take 5 powers away from each of them. Okay, this is a division. But if you look at the power, the division shows up as a subtraction. So I'm subtracting 5 from the power of each. So this becomes a 0, and then this becomes a 2, right? And x to the 0 we know is 1. So this becomes 5 times 1, and then the denominator becomes 1 times x squared. And how about the negative 2 and the negative 3? Yeah, the negative 3 is going to go to the top as a y cubed, and the negative 2 is going to come to the bottom as a y squared. And then how am I going to adjudicate those two? I'm going to subtract 2 from the power and get y in the numerator and 1 in the denominator. So at the end of the day, it looks like 5y over x squared. Okay, so let me go back and show you again how I did that really quickly. Oh God. My eraser is too big. Maybe I can make it smaller. Here we go. Maybe like so. Okay, so what did I do? I divided 15 by 3. I got 5 in the numerator. I took x to the 5th divided by x to the 7 using the power rule. That's x to the 5 minus 7, which is x to the minus 2. which appears in the denominator as an x squared, right? And then I do y to the negative 2 over y to the negative 3. You can subtract again. Negative 2 minus negative 3 is positive 1, I think. Okay, so that's how we get y in the numerator, with just 1 power. Any questions on these two examples or on any of our exponent rules so far? All right, then let's do a bit of an activity here. Oh yeah, first of all, if you feel like you need extra exponent review aside from what's in the homework, okay, then just send me an email. I have some like worksheets and stuff that you could work on to brush up on your skills if you feel like you're a little behind on exponents. So let's work with a partner for a little while here. We're going to try some integer exponents. God, I'm having real trouble with this thing today. So we're going to try some exponent stuff. Okay, so let's try to simplify these as much as possible. And then we'll come back together and discuss as a group. So go ahead and work with a partner for a few minutes here.
Are we allowed to use calculators on quizzes?
No.
No?
No, I'll make the numbers work out. But you'll need to be able to do like up to 12 times 12, you know, that sort
Oh
of
yeah,
thing.
because it's 2700.
Sorry?
The first one is 27. See,
Yeah, the first one's 27 times.
Yeah, you can leave it. Yeah, you can leave it like that. You can use a calculator right now if you want.
Okay.
Yeah.
No, I missed there.
No, it's. Yeah, because it's 2 plus 3, so it's 5. And 2 plus 3, 3. That's only
And then the next one we add.
Sorry? Yeah, 81. Yeah.
Oh, can you check that one else?
Yeah,
Yeah, it
sure.
did take a while. So we did that one, so then we distributed, so three cubed is 9.
3 cubed would be 3 times 3.
Oh my goodness.
27. Very good, very good.
I'm so sorry.
No, that's totally okay. Seriously, you don't have to apologize. So then, for 2 cubed, 2 times 2 again, right, which was 4, and then times 1 more 2 would be 8, right? And no worries.
I have to motion for this.
Okay.
No, no, why?
Now we're gonna do 27 times 8.
There you go.
I wanted to say
I'm so sorry, like, I am so nervous about this.
some of your friends.
Yeah, you can get down to like yeah, well, I mean, the last one was good, like, but yeah.
Does that say 81?
81, yeah.
And then just make it third.
Or you can,
I'm always ready. As you can see, I watch 40 minutes of the class.
All right, how we feeling? Would anyone like a little more time to work? Okay, yeah, take another minute or so and finish up.
Again, it's been a year or two since I've done this. So I've never tried this.
Yeah, so
I just got basic. I retook it too. I turned it
also
into
81 is 9 times 2.
I'm actually learning I was virtually at calculator pre-calc.
So it'd be 3 squared times 3 squared. So 81 is 3 to the 4th power.
Okay.
So then if we take 3 to the 4th power and divide it by 3 to the 1st power, then using our previous rule, we would subtract 1, right? So in the numerator, we would get 3 cubes, which is...
Okay.
Does that help you?
Not really.
Too abstract. Yeah, it's weird when you say it verbally.
Yeah. And I was just like, I'm kind of confused. I know it's simple. I just don't know what you
Okay, so we've got x to the 4 and x to the minus 5. Let's just handle that. So we are going to get the negative 1, right? So how are we going to do that? We're going to bring it to the numerator as to the 5th, right? And then how do we deal with x to the 4th minus x to the 5th?
We would add them.
Add the powers, right? Exactly, you got it.
These are going to be, okay, I might as well add this.
Well, if we have one of the two denominators, we just subtract. The thing is, this time, the denominator power is right? So actually, what we think is head right to the y squared, and the denominator is as y to the negative 2. And then if we dealt with, and then how would you do it? Y cubed times y to the negative 2.
I don't know.
So if we multiply y into something times y into something else, you have to add this one. So 3 plus negative 2 would be 1, right?
Yes.
Exactly. So at this time it stays in the denominator.
Okay.
Okay, we're gonna go through this other class in a second. And
I'm so
I think you'll see what I mean.
sorry.
No, you're fine. Okay, let's come back together as a class and talk these over. So there's a couple of things that you could do on these problems, and they might make it easier or harder than the ways that you did. So let's talk through a couple of strategies. So we just learned a bunch of exponent rules which tell us how to do, tell us how to rewrite these exponent things. So you can go ahead and do that if you want, or you could also go ahead and use PEMDAS, right? If we were to use our rule, in this case, we would get what? 3 cubed times 2 squared, 2 cubed, which would be the same as 27 times 8, right? Which we could go ahead and multiply, 27 times 8 like so. What do we do? 7 times 8, we get whatever we get, 56, right? And then 2 times 8 is 16. plus 5 is 21, right? So we can go ahead and multiply along like that if you want. Or if you use PEMDAS, I think it's a little bit easier to see that this, if we do PEMDAS, we're supposed to do the 3 times 2 first, right? So we could also just get 6 cubed, which 6 cubed is 216 if you have that memorized. I think it's easier to see 6 cubed is 216 than it is to do this multiplication, but that's also because I have a lot of cubes memorized. So the couple different ways to do that one. Any questions on the first problem? Okay, then the second one. Again, we could go ahead and try to FOIL this out 3 times, but I think the easier way to do it is probably to add these 2 first and then cube, right? So what do we get? 5 cubed, which is 125. Any questions on that one? Okay, and then 2 to the negative 3, that's just a straight answer. We know what that is. That's 1 over 2 cubed by our rule, which 2 cubed is what? 8. So this is just 1/8. Okay, so we got 3 numbers so far. And now for the meat problem, which is to simplify 81 over 3, x to the 4th times x to the minus 5, y squared divided by y cubed. Okay, so one thing that you can do in this situation, by the way, is break this up, okay? You have products in the denominator, okay, and products in the numerator. So if you want to, what you can do is break this up in the following way. 81 divided by 3 times x to the 4 over x to the minus 5 times y squared over y cubed, right? We can break it up like that because if we were to multiply straight across 81 times x to the 4th times y squared, that's exactly what this is. And if we were to multiply straight across in the denominator, we'd get exactly this denominator. So if you find it helpful to split it up like that so that you can see like what goes with what, then that's something that you can do. So let's start with just 81 divided by 3. So one thing that you can check is, you could check using a calculator to see whether 81 is divisible by 3. Anyone else know a trick for how we can tell whether 81 is divisible by 3 or not?
I guess it's 9 times 9 and 3.
It is 9 times 9 and 3 goes into 9. That's one way. Any other ways?
9, 8, and 1.
Yeah. If you want to tell whether a number is divisible by 3, you just add up its digits. If the sum of its digits is divisible by 3, then the number is divisible by 3. That's a number theory fact that you might have learned in like elementary school. That's like, you got to dig way back to find that one. Okay, so 8 plus 1 is 9. 9 is divisible by 3. Therefore, 81 is divisible by 3. But also, you can rewrite it as 9 times 9. So this is 9 times 9 over 3. And 9 is nothing but 3 squared. So this is the same as 3 squared times 3 squared divided by 3, which is the same as 3 to the 4 divided by 3 to the 1. And if I do 3 to the 4 divided by 3 to the 1, I just get 3 to the 3, right? Was that too fast?
No.
Okay, let me go back through that. So I rewrote 81 as 9 times 9. We all okay with that? Then I know that 9 is 3 times 3. So I rewrote the numerator as 3 times 3 times 3 times 3. And then I divided that by 3, so I took one of the 3's away. So I ended up with just 3 3's left in the numerator. Okay? Now let's talk about how to handle x to the 4 divided by x to the 5th, or negative 5. Okay, so since I have a negative power in the denominator, I can move this to the numerator as a positive power. Okay, that's what I'm going to do. I'm going to rewrite this as x to the 4 times x to the 5th. Okay? Because this is like dividing by a fraction. Dividing by a fraction is the same as multiplying by the reciprocal. So that's how I get this up to the numerator. And then I get x to the 9th. Okay? In the numerator. You could also use the subtraction rule, right? 4 minus negative 5 would be 4 plus 5, which is 9. So that's another rule that you could use if you wanted to. So this is x to the 9. Okay, and how about this one? How do I deal with something when the power in the denominator is bigger than the power in the numerator? Yeah, Griffin?
That's how I see it is the top one becomes a negative exponent. So then to make it positive, you put it as the denominator.
Yeah, so, okay, whenever the power in the denominator is outweighing the power in the numerator, okay, then we know eventually we're going to have a positive power in the denominator. And the sort of unwritten rule for simplifying these guys is that we want to, in the end, have only positive powers. Okay, so in the end, if we want to have only positive powers, we actually need to rewrite this by bringing the y squared down to the denominator as, so this is the same as 1 over y cubed times y to the negative 2. Okay, times y to the negative 2. And then now I can rewrite this using the sum rule, which says that y cubed times y to the negative 2 would be the same as y to the 3 plus negative 2. If I add negative 2 to 3, I get 1, which would just be 1 over y. Okay, so in the end, I'm left with 27 x to the 9 divided by y. Okay, that was by far the hardest one to do. So how do we feel about this? Let's have some thumbs. Thumbs up if we feel like I could do that on the quiz next week, and thumbs down if you feel like I don't like this problem. And somewhere in between if you're somewhere in between. Okay. Well, if you're somewhere in the thumbs sideways to the thumbs down camp, then I would say maybe shoot me an email or come to office hours tomorrow, and I can give you some extra resources to practice more of these simplification problems, because they're going to be pretty important just like throughout the class. So you might want to get a little bit of extra practice in just before we move on to some more complicated things. Okay. Questions about this one before we move on to something new? Okay, cool. Then we'll move on to polynomials. Okay. So we're probably going to start polynomials, and I'll give some definitions, and we might get into a little bit of factoring. We'll see. But the first thing we need to do is, if we're going to talk about polynomials, I should tell you what is a polynomial. Well, and the simplest polynomial ever is what's called a monomial. So if you ever took like a Latin class or a word within the word or something like that, then you know that poly means many, and mon means one, right? Okay, so this is the difference between a sum of many terms versus just one term. Okay, so a monomial is the simplest type of polynomial, and it has the form ax to the n. Okay, where a is a real number, but not 0. So I'm going to show us a little bit of crazy set notation here. Anybody remember what this symbol means? Not. It's the symbol we use for removal, okay, or set minus is what we called it. Okay, so if I take the real numbers and I remove from the real numbers the set of numbers which contains the number 0, then what am I left with? All the real numbers which are not 0. Right? All the real numbers which are not 0. So that's what this set is. This is a set. It's a bucket. It contains all of the real numbers that there are, except for 0, because I've removed it artificially. Okay, so a is a real number. And how about n? Well, if we're doing polynomials, then n needs to be a whole number. So I would say we'll use our W notation. So n needs to be, okay, there's a couple different ways people do this notation, but it should be something like 0, 1, 2, ... i.e., the terminology we usually use for this is a non-negative integer. Okay, I prefer to say non-negative integer than whole number because of the confusion between what we defined to be the quote-unquote whole numbers versus like what we typically think of as a number which is whole. Anyways, it's very confusing, which is why I like to say non-negative integer. Okay, so this is a number times x to a power, basically. And the power needs to be a non-negative integer, so like 0, 1, 2, no fractions, and no negatives. Okay, so the coefficient is what we call a, and the degree is what we call n. Okay, so this is a monomial with coefficient a and degree n. For example, 3x squared. Okay, 3x squared could be a monomial. Okay, or maybe let's get real crazy with it. Pi times x to the 17. That's also a monomial because the coefficient just needs to be a real number, which isn't 0. So there we go. And we could also use maybe the number 3. Why is the number 3 a monomial in this case?
Because it could be like x to the 0 power.
Yeah, it could be 3 times x to the 0, right? So you could think of 3 as 3 times x to the 0. We said that the power could be 0. It's just that x to the 0, no matter what x is always going to be 1, so we just don't write it, because 3 times 1 is 1. Or 3 times 3 is 3. Jesus. 3 times 1 is 3, is what I was trying to say. Okay, so those are monomials. So what is a polynomial going to be? Well, a polynomial is going to be a sum of various monomials. Okay, so for example, hello, x to the 7 minus x to the 6 plus 21x cubed minus x squared plus 31.5. There we go. There's a polynomial. Okay, polynomial is just a sum of various monomials. So one thing that we want to talk about when we're talking about a polynomial is we like to write them in what we call standard form. And by standard form, the only thing that we mean is, first of all, be sure to combine like terms. So what do I mean by like terms? I mean monomials with the same degree. Same degree. And second of all, write the sum in decreasing order of degrees. Okay, so for example, if we started with something like x squared plus x to the 7 plus 3x squared minus 1. If we wanted to put this into standard form, first we need to combine like terms, which what I mean by combine like terms is I have an x squared and I have a 3x squared. I know I can combine x squared and 3x squared to get what? If I'm adding them, I have 1 of a certain kind of thing, and I have 3 of that same type of thing. If I combine them, then I have 4 of that thing. It's like 1 apple plus 3 apples is 4 apples, right? So, and I also need to write it in decreasing order of power, okay? So 7 is the highest power that I see, so I'm going to write this as x to the power 7 plus 4x squared minus 1. Okay? So that's all that we mean by standard form. We mean make sure you combine all like terms and write this in decreasing order of degree. All right. Any questions on the definition of a monomial and a polynomial, as well as coefficients and degrees? Okay, so by the way, the terminology we would use here to describe this polynomial, we would say that this is a polynomial of degree 7. So when we refer to the degree of a monomial, well, a monomial only has one term. It's just whatever the power is. When we refer to the degree of a polynomial, we refer to the largest degree in the entire sum. Okay? So polynomial of degree 7. Okay, so let's see some examples of polynomials real quick. So one example could be maybe, I don't know, we've seen several so far. Can someone give me an example of another polynomial?
X cubed plus 2x squared.
X cubed plus 2x squared. Great. Let's have one more from someone else. How about I quiz you? Let's start with 3x to the 1/2 minus 2. Polynomial or not polynomial? Not polynomial. Why do we say not polynomial? It's a sum of different powers of x. The problem is the power is a fraction. Very good. Okay, I couldn't sneak that one by you. Is not a polynomial. All right, how about this one? E to the x. We got a number to a power. Sorry? It's not actually a monomial. What do we need for this to be a monomial? We need x to be raised to a number power. In this case, we've got a number being raised to the x power. Okay, so it's a little bit different. In this case, it's actually not a polynomial. This falls into a class of functions which we call exponential functions. Okay, so e to the x, or sine x, or I don't know, like a million other functions. Absolute value of x, something like that. All right, so another polynomial, I don't know, we could get crazy with it. E times x to the 13 minus pi. It's totally okay for us to have really weird numbers as coefficients. What is not okay is for us to have really weird numbers as powers. Okay, that's the only thing. All right, so let's talk about how we add polynomials together. So all we do is, I already said it, we combine like terms. Okay, so let's do a couple practice problems where we're adding polynomials. Let's do 3x squared minus 10x, and then we're going to add x squared minus 3x plus 2. Okay, so if I want to take two different polynomials and add them, then what I need to do is I need to combine like terms. Okay, and we have to be a little bit careful here, mainly in just keeping track of the sign of these different things. Because if I'm going to add an entire polynomial, I need to make sure that I'm adding x squared, but when I'm adding negative 3x, I need to be careful to pay attention to that sign there. Okay, so let's start with x squared. That's the first like term, right? I've got one that says 3x squared, and then I'm adding to it x squared. So what am I going to get? 4x squared. Okay, now comes a tricky one. I start with how many x? Negative 10. And then what am I doing? I'm adding negative 3x to it. So if I take negative 10x and I add negative 3x, what do I get? I get negative 13x. Very good. Okay, and then how about the last one? We've still got a plus 2 hanging out. And there we go. All right, let's do something more complicated. Let's do 3x squared minus 10x minus x squared minus 3x plus 2. What am I going to have to change about my strategy to accomplish this one, this harder one? I'm going to need to distribute the negative, okay? So you can think about that in a couple of different ways. You could literally rewrite it as plus negative x squared plus 3x minus 2, like so. You could rewrite it like that. Or you could just say, each time I'm going to remember that I'm doing subtraction here, and I'm going to do the following. 3x squared, I'm going to subtract x squared, I get 2x squared. And then I'm going to take negative 10x, I'm going to subtract negative 3x, what will I get? Negative 7x. And then I'm going to take 0, and then I'm going to subtract 2 from it and get negative 2. Okay, so do not forget to distribute the minus sign. All right, how about multiplying polynomials? Well, let's stop for a second. I don't want to go too fast here because we've been learning a lot about polynomials so far. So we learned the name of polynomials, we learned about coefficients, degrees, how to identify them, okay, and how to add them. Are there any polynomial questions so far just burning in your heart that you need to release? No? Okay, then we'll talk about one more topic before we close for today, which is multiplying polynomials. And the only trick about multiplying polynomials is we are going to need to use a certain property of multiplication that we learned earlier today. Does anybody know what it is? That's right. It's the distributive property, right? If I want to multiply two polynomials, I need to use the distributive property. i.e., we are going to multiply each term of the first times each term of the second. So what does that look like? Well, you can kind of think about it like this. We're going to do 3x squared times x, 3x squared times negative 1. We're going to do negative x times x, negative x times negative 1. And we're going to do plus 7 times x and plus 7 times negative 1. So we need to multiply every term times every term. So first we get 3x cubed. That's from 3x squared times x. Then minus 3x squared. That's from 3x squared times negative 1. Now, minus x squared comes from negative x times x. And then plus x comes from negative x times negative 1. Finally, plus 7x comes from 7 times x, and then minus 7 comes from 7 times negative 1. Every term of the first guy needs to be multiplied by both of the terms in the second guy. And now we're left with a bunch of crap, which what do we have to do to finish this off? Combine like terms. 3x cubed minus 4x squared plus 8x minus 7. All right, let's stop there for today. Thanks for your attention. And I have office hours tomorrow. If you feel like you're getting a little bit behind, please make sure you come to office hours tomorrow and get ahead of it early. I promise you will be happy that you did so.